Okay, let's get straight down to it. 28 out of 50 was the average for this one. You need your own copy of the paper because well, I'm not allowed to show it. Full electron configuration for chlorine. Now don't be doing 287. That's the electron arrangement. That's not even IB anymore. The electron configuration. So here's chlorine. It's got 17 electrons. So I'm just going to wander along. 1s2, 2s2, 2p6, 3s2, 3p5. Double check. Should be 17 electrons. 2, 4, 10, 12, 17 electrons. Yep. And chlorine should be in the 3p5 position. That's period 1, it's period 2, it's period 3. Yes, so it's going to be in the third row. That's what the 3 means when it comes to the P block. And this is the P block, and it's the 5th one along. 1, 2, 3, 4, 5. Lovely. Next up. Half the people got this right. Chlorine or chloride has the larger radius. If only half the people got it right. Doesn't speak much, does it? So chlorine versus chloride. Well, I know that chlorine is, well, you know what? I'm going to say 287. Still accepted here, but you wouldn't want to give it as your full answer. And 28, well, that's chloride, 8. So just having a quick list underneath, you've got electrons, protons, and neutrons. Well, I don't care about the neutrons. Chlorine has 17 electrons and 17 protons, but the chloride has 18 electrons and 17 protons. So what that means is they have the same number of shells, but because the chloride has that extra electron in the outer shell, it's going to repel with all the other electrons, and it's actually going to be bigger. So the chloride ion is bigger because the extra electron causes the other electrons in the shells to repel, inflate it, if you will. How many points was that worth? Just 1. Was that enough? Yeah, chloride and more repulsion. You could have just said that. Right then. Next up, 1AII, 30% correct. Why is chlorine smaller than sulfur? I bet that's 2 points. Yep. It's always 2 points. So sulfur and chlorine. Well, if I zoom in, sulfur has 3 shells because it's in period 3, but the chlorine also has 3 shells. So you can't say, chlorine's got a different number of shells. That's not true. You can't even mention the number of shielding electrons because sulfur has 2 here and 8 there. Chlorine also has 2 there and 8 there. They have 10 shielding electrons that are between the valence shell and the nucleus. So where are my 2 points? Well, for chlorine, there are more protons and more electrons, so there's more electrostatic attraction. Yep. Chlorine has 1 more proton and 1 more electron than sulfur. It's 1 point. But then you do need to say they still have the same number of shells. That's the second point. Because just having more protons and electrons doesn't make something smaller. If you look down here to selenium, that has more protons and more electrons, but it's actually bigger than sulfur. Why is it bigger then? I thought more protons and more electrons were smaller. Well, if they had the same number of shells, it is smaller. But selenium has 1 extra shell. 1, 2, 3, and then it's the 4th shell. That should be my 2 points. Same number of shells, and chlorine has the greater number of protons, attracting the electrons. Lovely. You didn't even have to say electrostatic attraction. They seem quite keen on that now. That means there are protons and electrons attracting each other. Okay, next up, 1IV. Why are there 2 peaks? Well, the 2 peaks are isotopes, aren't they? These ones here. DIB complained that people said isomers. No, isotopes. Atoms with the same number of protons, different numbers of neutrons. Isomers. Atoms, molecules with the same formula, different structure. Next one was supposedly the hardest question. What is this going on at 74? Well, you had to know that chlorine is diatomic. That means chlorine likes to come in pairs. How could you possibly know that chlorine comes in pairs? Well, hopefully you know that, but if you didn't, there's something called Brinkelhoff that will allow you to remember. Brinkelhoff. These are the diatomic elements. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So there are those three peaks at the end here. So what's going on? Well, if it's the 35-35, that's going to give you the peak at 70. If it's the 35-37, that's the next peak. But the one we're looking at is the peak at 74. So that's going to be 37-37. So that's 1 point for noticing that. But they also ask about the relative abundance. Why is that the smallest peak? Well, because chlorine 37 is the isotope with the lowest abundance. Well, how are you supposed to know that? Well, I mean, there it is, isn't it? We just gave you the mass spectrum. So that's where the 2 points are there. 1b. Okay, so the IB expects you to use all the decimal places in their periodic table, but you know what? They really, really care about that. If they don't say it, then you probably don't have to. You can just use integers. All right, the moles of manganese 4 oxide. So I like to use the grid method. Manganese 4 oxide. Got 54.94 and 16. So 54.94 plus 16 plus 16. So that's going to give me 86.94. 86.94. And the mass is given to me 2.67 grams. So moles is mass over molar mass. So 2.67 divided by 86.94. So that's going to give me 0.0307. 0.0307. I'm trying to keep 3 Sig Figs here because of the 2.67 in the question. So that's the answer to the first question. Is that right? Yep. I didn't put moles, which is a bit cheeky. Sometimes I take a point off, but in this case they asked for it in moles in the question, so you'd never lose a point for that. Next up, the limiting reactant. All right then. So for the limiting reactant, the boxes don't really work, which tells you it's an excess and limiting question. So I need to know how many moles of hydrochloric acid I've got. So since it's a solution, I bet they give me the concentration and the volume in the question. They have. So moles is concentration times volume. You have to memorize that. The concentration is 2.00 and the volume is 200, but you've got to divide by 1,000 because you're in decimeters cubed. I can do that in my head. That's 0.400. Now in this case, it seems quite obvious to me that there's much more of the HCl compared to the MnO2. And that indeed, the MnO2 is the limiting, but sometimes they give it to you with numbers that are pretty close. So you have to do the maths. Well, let me show you how to do the maths. So what you do, just in case it's not obvious to you which is the excess, too much, or the limiting, not enough. So I'm going to do 0.307 divided by 1 and 0.400 divided by 4. Where did I get those numbers from? Well, this one is there. And there's the 4. So I did the moles over the coefficient. Which one's lowest? That's the limiting. Oh, we get that 0. Otherwise that won't work. Okay. And which is the lowest? That's the limiting. Well, it looks to me quite clear that that's the lowest one. So the lowest is limiting. So calculate, determine the limiting reaction. There we go. So by comparing the moles over the coefficient, I can clearly show that MnO2 is limiting. Next up, the excess amount of moles of the other reactant. Now don't go crazy and fill all the boxes. I've got kids that still do that. Fill everything in. The exam's over. You've got one pretty box. All right then, so I know that this is wrong. It's excess. It's wrong. Excess. It's wrong. It's too much of it. So what should that number be? So 1 is to 0.0307 as 4 is to x. So I have to solve for x. So that's just going to be 4 times 0.0307 so 0.123. Now that isn't enough for the point. That's just enough. That's how much you actually used. I'm sure you haven't got your point. So how much extra did you put in? That's the question. Well, you put in 0.4 and you used 0.123. So the excess that you used must be the difference. Most people could do, half the people could do this. So I put in 0.400 moles and I used 0.123 moles. So my excess is going to be the difference. What's that? 0.277? No, 287. Yeah. 277. There we go. That's the answer. That's the 1 point. I worked quite hard for that. Next up, calculate the volume. 60% of people got this correct. Now, when it says STP for gases, that probably, almost certainly means you don't have to do the PV equals nRT. It would get you the same number, but if you look at the data booklet, STP for gases is the 22.7. So 1 mole is 22.7 decimeters cubed. So if I had 1 mole of chlorine at STP, it would be 22.7 decimeters cubed. If I had 10 moles of chlorine, it would be 227 decimeters cubed. All right, how many moles do I have? I don't know, I have to work it out. Oh, it's easier than it looks. 1 is to 0.0307 as 1 is to 0.307. Oh, so the ratio at the top there's trivial. Oh, come on, fat fingers. 0.0307. So that's how many moles of chlorine I've got. So I've got 0.0307 moles, and I know that 22.7 decimeters cubed is 1 mole at STP. So does my units go to give me a volume? Nice. So what's that going to be? Let's just divide that by 4 to get back to where we were, and multiply by 22.7. Okay, moving on. Oxidation states should be a piece of cake. So oxygen in a compound is -2. They could have tricked us there because the exception is oxygen and H2O2 where it's -1, -1. I think that was in the multiple choice, that trick. And so manganese is going to be +2 because they all have to equal 0. How do I know it's 0? +4, idiot. How do I know it has to be +4 there? How do I know they all equal 0? Well, whatever the charge is what it finally equals. And there's no charge, so it's going to be 0. Chlorine is a halogen, and that's going to be -1, probably, leaving manganese as +2. If you put 2+ or 4+, you'd lose the point. If you put Roman numerals, you'd lose a point. All right then, so I've got +4, and it turns to +2. And so the number goes down. That's going to be reduction. Makes sense, doesn't it? And so I think an oxidizing agent is itself reduced. So that's going to be the oxidizing agent. You can't put OA. The IB doesn't understand that. You have to put oxidizing agent. So it's the oxidizing agent. Because it goes from +4 to +2. 50% correct. That's kind of sad, since it's a 50-50 question somewhat. Next up. Chlorine and equilibrium. 80% correct. A weak acid, you just had to learn this by rote. It's partially dissociated. Partially dissociated. I don't think they care that it has to be in water. No, they don't care if it has to be in water. The formula of the conjugate base of hypochlorous acid, 50% correct. So I think a conjugate acid is made by adding a proton. So a conjugate base has to be the opposite. It has to be by removing a proton. So the conjugate base of this is going to be ClO minus. Lovely, 1 point. Calculate the concentration of H plus ions. They said this was done well. So you could check out the data booklet. I'm sure it's got the pH thing there. What's that? Topic 8. Yes, it's one of these equations, isn't it? For the pH. So I remember pH equals negative log H plus. But it looks like we need the other one, which is H plus is 10 to the negative pH, which in this case is going to be 10 to the negative 3.61. Can you just leave it like that? Nope. They don't give you a point for that. Let's try it on the calculator. All right, so that's going to be 2.45 times 10 to the negative 4, and that's concentration. What are we looking at there? Concentration. So we're probably going to have to put the units in. Concentration comes out at moles per decimeters cubed. They got 2 Sig Figs. I don't think that's going to be a problem. I put 3 because I've locked into that. Who knows? Alrighty. Next up, calculate ethane with chlorine to produce chloroethane. I have kids come out of exams and say, Mr. Fornelly, you never taught us that, you never taught us that. Ethane doesn't react with anything because it's non-polar, so there's no place for plus or minus things to attack. It's got strong bonds, we never did it. And I just say 3 words: initiation, propagation, termination. Oh, I remember that now. So it's that stuff, isn't it? So what's the type of reaction? So that was free radical, wasn't it? It was free radical. Remember you put those dots everywhere? And you were actually swapping out chlorines and hydrogens. So that's substitution. So free radical substitution. Remember it only happened in sunlight. You have to you have to shine ultraviolet light on it to get it going, to break the chlorine bond. Free radical substitution. That's it. You didn't even need the free radical. You just needed the substitution. Next up, what's more reactive, ethane or chloroethane? 30% correct. I think I just covered that. So ethane is non-polar. That means there is nowhere for anything a little positive or a little negative to attack. No room for electrophiles or nucleophiles to come in. But the chloroethane, well, that has a honking great big chlorine at one end, doesn't it? So chlorine has a high electronegativity compared to the carbon. So the electrons are going to be dragged down that one end. So this end's going to be a little bit negative, which means it's going to be vulnerable to attack by things that love negative things, so electrophiles. And this bit here is going to be a little bit positive. So it's going to be potentially attacked by nucleophiles, things that love positive. So it's going to be more reactive. It's the chloroethane. What's their answer? You could have had that the bond is weaker between carbon and chlorine. I quite like that as an answer too. Okay, the next few questions are a not very visited part of the syllabus. Chloroethane and dilute sodium hydroxide. Draw that out. So I've got chloroethane. Eth is 2 carbons. Chloroethane. That's there. And, I'm just going to say the hydroxide ion. You could put sodium hydroxide, but hydroxide ion is acceptable. So what's going to happen there? Well, if you don't know, then maybe you could intuit what's going to go on. This is negative, and the chloride is a little, the chloro's a little negative there, which must mean the carbon's a little positive. Don't forget the chlorine's dragging electrons over towards itself. So chemistry, negative attacks positive. So it looks like that this is going to attack the carbon. Well, it can't just stick on the carbon, because then carbon would have 5 bonds. So I bet the chlorine drops off. And in fact, that is what happens. So it's just 1 point, but you're going to make ethanol and Cl minus. So that's 1 point there. The next question, what's the nucleophile? Highly discriminating. Only the smarties got it right. Well, you've only got 2 choices. It has to be either that or that. So let's think of the word nucleophile. Nucleus is positive and something phile is love. So something that loves positives. So what loves positives is going to be negatives, isn't it? It's going to be negatives. And so it's going to be the hydroxide ion. And that's the correct answer, the hydroxide ion. Okay, let's draw ethoxyethane. So that's an ether. Ethers have a carbon, oxygen, carbon. And the eth also means, curiously, that it has an ethane kind of stuck at each end. So methoxymethane would have a methane stuck at each end, but ethoxyethane has an ethane stuck at each end. Next up, the H1NMR. So H1NMR detects 3 things about a molecule. The number of hydrogen environments gives you the number of peaks. The ratio of the hydrogens in those hydrogen environments gives you the area under those peaks. And the location on the spectrum tells you about that hydrogen environment. Is it an alcohol? Is it in a carboxylic acid? Where is it? So they just want to know the number of signals, first of all. Well, I can see there's 2 hydrogen environments. This. That's 1 hydrogen environment, along with that. So those 6 there are in the same hydrogen environment. The second hydrogen environment is that one and that one, and that one and that one. So there are 2 different hydrogen environments, so there are going to be 2 peaks. So that's your first point. 2 peaks. What is a hydrogen environment? You've got to look at the other video. It's too complicated to explain here. Now, where are those peaks going to be? They don't actually want to know the ratio of the area under the peaks, but it would be 6 to 4, because there are 6 hydrogens in one environment and 4 in the other. All right, so I can see this is clearly CH3. So that's the first peak, or the chemical shift. Now, it's tempting to say that's the second one, but don't forget we had that oxygen, that ether. So let's scroll through and find ethers. Yes, there's the ether here, isn't it? That's the ether. So 3.3 to 3.7. So those are the 2 peaks. I've got one between 0.9 and 1.0, and another between 3.3 and 3.7. Is that right? Yeah, you need both of them to get the points. And I forgot the units, but this time the IB forgave me, ppm. Next up. This was the easiest question, the percent of chlorine in difluoromethane. Okay, so first of all, we need to work out the molar mass of that. So without looking it up, I think I can do it. So it's 12.01 plus 2 times 35.45 plus 2 times 19.00. Why am I lagging? I think I was just humming the Squid Games. Oh, that's a weird show. My wife made me watch it. All right, let's work out the molar mass of that then. So 120.91. So the total molar mass is 120.91. I'm going to quickly check if that's right. Yep. And then the percentage of chlorine, well, I can see there's 2 chlorines here. So I better account for that. So at the top of this is going to be 2 times 35.45 and multiply by 100 to get a percentage. All right, 58.64, 58.64, 58.64. We're going to do Sig Figs and stuff like that. I think probably 4 Sig Figs is enough, because I can see I've got 4 Sig Figs there. Are they going to complain about the Sig Figs? No, that's okay. As a rule of thumb, you can be 1 Sig Fig out each way and they'll let you off probably. And another rule of thumb is if they want the Sig Figs, they'll probably tell you, but no one's quite sure. It changes each year. Now, rather stupidly, I forgot the percentage, but they would let you off as well with that. Oh, that was the easiest question. International cooperation, same question every time each year. International cooperation, so a diversity of viewpoints. You have more people to repeat your experiments to see if they're right. You have more people to try different experiments to see if you're wrong. There's a whole bunch, but I like the diversity of viewpoints. That's the one. That's the quickest one to vomit out here. Collaboration, technology shared, political pressure, passing legislation. Uh-oh, do not accept. Did they change that? Do not accept just collaboration. Arguably the most successful international agreement ever was the Montreal Protocol that banned CFCs. Okay, question 2A. I misread this the first time. It's the electron geometries and domains around the oxygen atom. I just did it around the carbon. That was silly. All right, so let's look at the oxygen. There's actually a bond and 2 electron pairs on that oxygen. So there are 4 electron domains, and so the electron domain geometry is going to be tetrahedral. Tetrahedral. And what about the actual geometry of that part of the molecule itself? Well, it looks bent, and it is actually bent. If they ask you to justify why you're saying it's bent, because anything with 4 electron domains with 2 lone pairs is going to be bent. Let's take a sidebar. What about, isn't it linear, Thornley? Everything looks like it's in a straight line there. No. It's tempting to say it's linear, because these 4 electron pairs are as far away as possible, but that's 2-dimensional. We live in the 3-dimensional spatial world, so it's going to come out as bent. Next up, again, this one I did wrong. So fast forward if you don't care about how I got it wrong. So infrared measures the different bonds, the carbon bromine, the carbon oxygen, the oxygen hydrogen. So I just counted up 1, 2, 3, 4 troughs. So there must be 4 sorts of bond. And I just used that and I worked it out as all wrong. No. Apparently that isn't how it works today. So we're going to check so let's check the data booklet, zoom down to infrared, and hopefully it's just checking stuff out. Alrighty, so let's pick molecule B. What looks distinctive in B that isn't in A? A carbon-oxygen double bond. Let's see if we can find that. Yep, carbon-oxygen double bond, and that's going to be at 1700 to 1750. Yep, and that's there. So 1700 to 1750 is this peak. Let me just check it on the real diagram. Yeah. Okay, so unambiguously it's B, because B has a trough, not a peak, a trough at 1700, 1750, which is the carbon-oxygen double bond. So that's the answer for that one. You needed both of those ideas for the point. Another isomer, C3H6O. So if it was C3H8O, I'd know I could have propanol and this. So there's not enough hydrogens as I expect, so I bet there's going to have to be double bonds. So that's my first guess. Let's put an alcohol there. 1. 1, 2, 3, 4, 5, and then 6. So that's 3 carbons in a row with an OH at the end. Okay, so that's different. That's different to this one here. That's got an OH in the middle. Let's do another one. We can do an ether, can't we? I've got to probably have another double bond somewhere there. 1, 2, 3, 4, 5, 6. So an ether with a double bond. Let's check the answers. Yeah, that one and that one. Just to make sure everything's working, every carbon's got 4 bonds, oxygen's got 2, hydrogen's got 1 bond. Yep, all good. 2D, Kc, the equilibrium constant. There are questions I love to ask about that. It was the only thing that changes Kc is temperature. So they'll go, oh, what if we double the concentration of A? What does it do to Kc? Nothing. Now, you could flip the equation. That would invert Kc, but they really ask those questions. So the only thing that changes Kc for an equation that's in front of you is temperature. Okay, so Kc is the concentration of products over the concentration of reactants at equilibrium. And since Kc is huge, that must mean that at equilibrium, there's way more products than reactants. So is that the question? Deduce what's greater concentration. So there's a greater concentration of products, and the products is B. And why is that? Because Kc is greater than 1. So they could have asked you another tricky question, but they didn't, which is, okay, there's loads of B, there's not much A, so which reaction's going faster? It's equilibrium. They're going at the same rate. On to question 3. Combustion of propane, so that's basically lighting the lighter. Find delta H theta using section 11. Okay, so section 11, is that bond energies? You know what? I know I can do bond energies, and I just can't do them right every time. I make a stupid mistake because I get impatient. Okay, so these are average bond energies. It only works if everything's a gas. So sometimes they force you to do it when one of them isn't a gas. And then they go, well, that didn't work. And then you go, has to be a gas. They're all a gas. So what I'm going to try to do is I'm going to, let's make a bit of space. Underneath here, I would leave this question to the end just because it takes way too much time. So oxygen's a double bond, so I need to account for that. Carbon dioxide has double bonds in it. Water, single bonds. And this is propane. Now, if you make a mistake along the way and you've shown your work, you'll probably get partial credit. They're a little bit fussy how they like it set up. So let's put those numbers in. I like to say on the reactant side, you've got to break everything up to make the atoms. So breaking everything up is endothermic. So that's going to give me positive numbers. So these numbers here have to be positive. But when you're making bonds, I remember making bonds is exothermic. I can feel the heat. As I make the bonds, I can feel the heat. So those are going to give you negative numbers. And once you've worked out those numbers, just add them up. Your teacher might do it a different way. Good for them. So that looks good. It's negative, it's exothermic, it's burning fuel, so I'm pretty happy with that. Okay, question 3b, use section 12. So this is just another way. There's 4 ways to measure delta H. In SL, 5 ways to measure delta H. I forgot about the energy diagrams. So section 12 is to do with the standard heat of formation. So to work out delta H for a reaction, you're going to do the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. And there's always 2 tricks. I can see them already. The first trick is when you're going to go to the data booklet to look at the heat of formations. I've actually been called into an exam once before. There is no value for oxygen. It's 0. The standard heat of formation for oxygen is 0. And I'll tell you why. The standard heat of formation is making 1 mole of the substance from the elements in their standard state. So you can see that nothing is happening there. Making 1 mole of a substance from the element in its standard state, everything's just the same. So that's going to be 0. And the other trick, which I know they're going to put in, is there are 2 values for water, liquid and gas. So we have to make sure that we use the gas value, because that's what's in the question. All right. So propane is minus 105. And let's see if I can memorize 241.8. Carbon dioxide. All right, let's take those values and see, put them into that equation. Right. Okay. So I got it right. How many points is that? 1,000? Just 2 points. I got so excited that I forgot to check my Sig Figs, but it seems to me we're adding, so there should be no decimal places. How do I get that? Because there's 1 decimal place here and no decimal places there. So my answer should have no decimal places, which is minus 2043 kilojoules. How do I know that that's right? Well, I'm pretty sure it's right because it's basically a different way of getting the same answer as up here, and the answers are similar. Okay, 4A. Let's keep going. Oh, I thought I'd gone back again. So 4A, how does a catalyst increase the rate of reaction? So you can say it provides an alternate reaction pathway or it lowers the activation energy. Those are the 2 IB answers. Oh, you needed both for the point. That's cheeky. That's cheeky. So since normally that's 1 of those for the point, and now you need both of those, I think this exam must have been a bit easy, so they're trying to make the exam a little harder than the mark scheme. So alternate reaction pathway with a lower activation energy for 1 point. B, they always ask about temperature. There are many different ways you can change the rate of reaction, but temperature is the one the IB likes because it involves 2 of the 3 parts of collision theory. So to recap, collision theory, it's to do with the frequency of collisions of the reactants, the geometry of those collisions, and how many of them have energy equal to or greater than activation energy. So for temperature, it ticks off 2 of those. So increasing the temperature means more collisions per unit time or more frequent collisions. You can't just say more collisions. You have to talk about the frequency. And also, each of those collisions is more likely to have a higher energy. So higher energy collisions. So that going to get us to 2 points. More collisions per unit time. And greater proportion of molecules with energy greater than activation energy. There we go. So more of them have energy greater than activation. Energy greater than activation energy. More of them have that. You'd have to write that down. And more frequent collisions. More frequent collisions. Okay. Next up, 4C. So propanone is a ketone. And propan-2-ol. No points for joining them, because that's not the question. Okay, intermolecular forces, relative volatility. All right then, so this is just the same old, same old. You can see that this has the ability to make a hydrogen bond. This isn't a hydrogen bond here. A hydrogen bond, that's a covalent bond. A hydrogen bond is between one molecule and the other. So propan-2-ol can make hydrogen bonds, which is a stronger intermolecular force than propanone, which has a dipole. Because the molecule is bent, and oxygen's at the top, and oxygen has the highest electronegativity, loves electrons the most. So which is going to be the most volatile? Is that the question? So volatile means the ease that it can turn into a gas. So the propanone is more volatile because it has a weaker dipole-dipole bonding than propan-2-ol, which is less volatile because it has stronger hydrogen bonding. Now, of course, anything with electrons has London dispersion forces, so they both have London dispersion forces. So occasionally the IB says give all of the intermolecular forces. In this case, you didn't need to mention the London dispersion forces. They're the weakest. So the other two we talked about, dipole and hydrogen bonding, is just so much of a larger magnitude, you could ignore them. 4DI, Voltaic Cell. Right. So it looks like the trick is, if you can work out what the negative electrode is, then everything else should just fall into place. The negative electrode is the metal that's giving off electrons. That's why it's the negative electrode. So you have to work out, is it the lead 2 plus, or is it the nickel that's giving off electrons? And I think it's pretty clear that the nickel's giving 2 electrons to the lead 2 plus. So knowing that, if you will, nickel is the most reactive metal, it's giving off electrons. I know that this must be nickel, and this must be lead. Because nickel is giving off the electrons, and that is the negative electrode. And for a half cell, well, you put nickel into the nickel 2 plus solution, and lead into the lead 2 plus solution. You probably did this with zinc and copper. We'd never do it with nickel, carcinogen, and lead, neurotoxic. So the IB's chose one they know you definitely didn't do, because it's terrifying. Is that right? Yeah, no, I didn't put the state symbols. They're not going to ding me for that. No, they're not. Suggest a metal that could replace nickel in the new half cell and reverse the electron flow. Oof. So section 25 of the data booklet. 25 is the standard electrode potentials. So initially we've got nickel and lead. Nickel and lead. And they say you want to replace the nickel with something and it makes it go backwards. So common sense would say if you've got nickel and lead and you want to swap the lead, you want to swap the nickel with something and it goes backwards. It has to be something below lead to make it go the other way for a complicated reason. So what metal below lead? I can see copper, iron, silver. Any of those? Copper, iron, silver. Nice. Okay, so that's the answer. Most people got that, so I don't feel I need to thrash that. Let's just say silver, Ag. Next up, describe the bonding in metals. So it's always positive metal ions in a sea of delocalized electrons. But that's for 1 point. This is 2 points. So they want another thing. Positive metal ions in a sea of electrons. They want me to draw it? No. So for the second point, often it's electrostatic attraction. The sea of electrons, delocalized electrons, are negative and they attract the positive ions. So I bet that's the second point. Yes, electrostatic attraction. Lattice of positive metal ions, sea of delocalized electrons. That's it, exactly. So always look out for that second point. Nickel alloys are used to suggest a physical property altered by the addition of another metal to nickel. So you can't say, maybe it changes the conductivity because that doesn't matter for aircraft gas turbine engines. So you could say maybe it alters the hardness of the metal, the flexibility of the metal, maybe the ductility, maybe the malleability. I would think anything would do. Except any physical property. Yeah, okay. So there we go. So I'd say it's going to change the hardness of it. They're not asking you to explain how alloys work, but they have done in the past. And we're done. Oh man. Didn't enjoy this one. But I thought it was fair. We're done. I said that.